All right, we're going to go ahead and get started. First things first, the survey gift, which, as I mentioned yesterday, we've had a fantastic turnout for. Is Ronald Spencer in the room? All right, Ronald Spencer, you win an iPad mini on behalf of Nanoc. Come grab it if you'd like. And I'd like to invite Martin Pels up to tell us about ARP mitigation at AMP6. Thank you.
Clicker? Okay. So hi, I'm Martin. I work for AMP6, and I'd like to talk a little bit about what we've been doing at AMP6 to reduce the amount of ARP broadcasts on our network. So the AMP6 ISP peering VLAN is a layer 2 broadcast domain implemented as a VPLS instance on top of an MPLS network. We currently connect over 700 routers to this. And this number keeps on growing. We added about 90 last year. Currently we were at 75 in August, so we expect to have 100 new routers for this year. And obviously all these routers need to talk to each other. And for that they use ARP. So we see quite a bit of ARP broadcast traffic on the exchange. The base rate is about 60 kilobits per second, but that is with our ARP sponge activated, which I will talk about. In case of an outage, it might be even more. So the issue is with all these routers that the moment a router goes down, everybody will start seeing this router disappear, and MAC address will disappear from their ARP cache, and they will start sending ARP requests for it. And if you have a lot of peers for this router, you will get a lot of ARP requests. So the more peers you add, this will increase exponentially. So to reduce the amount of broadcast ARP, we implemented a tool called the ARP Sponge. And this is a little piece of Perl software that runs on a device attached to the platform. And what it does is it listens to ARP requests coming in from other members for IP addresses. And when it sees a lot of ARP requests for a certain IP, it will start answering for this IP address to take over its IP address. Then once the down router comes back, it will start answering for itself again, and then the ARP sponge will stop. This makes a lot of difference. If you look at the previous slides, you can see this spike. This is when the ARP sponge was down for a maintenance, and you can see that the amount of ARP is a lot higher. Another thing that we do with the sponge is we don't just sponge the IP addresses that are assigned to customers if they are down. We sponge the entire /2022 subnet, and this is so that we also catch ARP requests for other IP addresses in case of things like ping sweeps. Now the ARP sponge works pretty well for us. It allowed us to scale the platform to what it is now. But we run into a couple of challenges. First of all, the CPU use of customer routers, the baseline CPU use is an issue because, well, the more routers you add, the more ARP, and ARP gets processed by these router CPUs. Then there's the ARP cache of the customer routers. We will be migrating to a /21 in a year or so. This will mean that the ARP sponge will start answering for 2,000 IP addresses, which is about half of the next hop table in some router implementations. We could, of course, fix this by not answering for IP addresses that we didn't assign, but that means we will get more ARP broadcasts for ping sweeps, which will again cause more CPU load. Then there's a CPU use in our own piece that we want to limit because they also process broadcasts on their CPUs. And we'd like to prevent ARP spoofing. We do not see any intentional ARP spoofing on our platform, but we do see the occasional software bug. So how do we do this? Well, SDN and OpenFlow can fix everything, so we figured we could try it with that. But we had a number of requirements here. We wanted this to be implemented as an addition to our existing network. We have an existing MPLS network. We don't want to completely replace that with OpenFlow, because if we would do that, we would lose all kind of features that we use now, and that would be more of a step back. We also wanted it to be scalable, of course, with the growth of our platform. And it has to be stable. We don't want to introduce any single points of failures, and we don't want the user-generated traffic to have an impact on control functions on the routers. So the work we did is based on OpenFlow version 1.0 as implemented by Brocade. Our entire platform is based on Brocade MLX, and we tested with a 5.5 beta release of their software. So the first thing we looked at is how can we implement OpenFlow as a feature in our existing network. And for this, the OpenFlow spec defines something called OpenFlow Hybrid, which you can use to either route traffic to your OpenFlow pipeline or to your normal pipeline. How this classification is done is not actually standardized. It is up to the vendor's implementation. And in the case of Brocade, this was done pretty neatly. What you can do per port is say if you have traffic that matches an OpenFlow rule, you send it into the OpenFlow pipeline. And if the traffic doesn't match, you send it into the normal pipeline. So what we can do in this case is set a very simple OpenFlow rule saying, for example, send all the broadcast traffic with either type of ARP, send that all to the controller, and forward all the normal traffic that doesn't hit the OpenFlow rule in hardware using the normal MPLS pipeline. So once you do that, there's a couple of ways you can handle this broadcast traffic. We've looked at solutions with controllers. We've looked at solutions with the ARP sponge that we already have. And there's also a way to do this by directly forwarding it to the right customer router by modifying it. So the most easiest solution is you send everything to the controller. We already have a database of all the IP addresses we assign to customers, obviously. We also have in our database all the MAC addresses of every customer, because we use that for our layer 2 ACLs. So what we can very easily do is have a table in the OpenFlow, in the controller, that has a mapping of all IP addresses to MAC addresses. Then if there is an ARP request coming in, we just have the controller answer it, and then everything functions normally. There are a couple of issues with this. One of this is that when a router goes down, the controller will still answer for it. And we cannot take into account migration scenarios where there might be two routers of a customer connected, and we don't know which IP address on which router the IP address is configured. So in that case, the controller wouldn't know with which MAC address to answer. So we can extend this a little bit further by having the controller act as a sort of proxy, by having the controller forward the ARP request as unicast to the right customer. It knows the MAC address, so it can send that as unicast. And then have the customer answer to the controller, and the controller to the party that sent the original request. Then if we take that another step further, we can have the ARP sponge forward the controller forward the request to the right customer, and set the ARP sender hardware address to the MAC address of the original requester, thereby causing the destination to answer on the ARP request directly to the requester. So you think, well, then that's pretty easy. It's a simple solution. It removes all broadcast traffic from the platform. We built a proof of concept using the implementation. It worked until we started looking at what it actually means if you do that for 700 routers on the platform. So the issues that we found is that first of all, you need an always active controller. That you can solve with having multiple controllers and having them both answer, or having the active one answer and doing a fallback. But a bigger problem is that, at least on Brocade, controller traffic is CPU forwarded. And in practice that means if you have 1,000 frames per second coming in from a customer that have to go to the controller, your management CPU will go to 80%, which is not really acceptable. And in addition to that, we didn't have any way to rate limit traffic sent to the controller, so we couldn't say per customer how many broadcast packets they could throw to the controller. So this pretty much ruled out this solution. Then we looked at other ways to do this, and obviously we already have the ARP sponge. So one thing we thought of is, well, then let's just forward all the broadcast traffic with the flow rule to the ARP sponge and have the ARP sponge reply to all the ARP requests. This has a couple of benefits. We no longer have any CPU forwarding on the PVE. We do forwarding with the flow rule, so there's no dependency on the controller except for programming this flow rule. Of course, it requires the ARP sponge to always be active, but again, you can have multiple ones. It also requires routers to ignore the source MAC address in the Ethernet header, because it will be different from the source hardware address inside the ARP request. We are not aware of any implementations that have a problem with this, but this is something we need to do more research on. It also requires support for the normal virtual output queue. This is an OpenFlow feature where you can take packets, send it into OpenFlow, modify it, and then send it back into your normal pipeline. That way we could have we could modify the destination MAC address to that of the ARP sponge, and then we could send it back into our normal MPLS pipeline and have it forwarded like any other packet. And here it would be nice to have some OpenFlow metering to rate limit the ARP traffic. Then a last solution we thought of is instead of sending everything to the ARP sponge, as I said, we know the IP addresses and we know the MAC addresses. So what we might as well do is take flow rules for every single customer, and once we get an ARP request, take the destination Ethernet address, replace it with the right unicast address, and forward the request immediately to the right customer. And then that customer replies, and we will be done with all broadcast traffic. We think this solution is the most simple. It requires no dependency on the controller except to program a flow rule. We won't need the ARP sponge anymore. And we could extend this to also set flow rules that allow certain ARP replies, and thereby we can prevent things like ARP spoofing. There are a couple of caveats here. Requests for routers that are down are still flooded because, well, it will be converted to the MAC address. The packet will be converted and sent to the MAC address of this router that is no longer available. One advantage is that the packets will be forwarded as unknown unicast. That means that routers for which the packet is not meant will be able to drop it in hardware. They don't have to process it on their CPU. What we could also do is disable hardware aging on our platform, which would allow us to always keep the MAC address entries in the CAM tables. And if a customer router goes down, these broadcast requests to unknown unicast destinations won't be forwarded over the entire platform. We would still need to use broadcast sometimes in case of migration scenarios when we don't know which customer router an IP address is tied to. We can remove the MAC flow entry for this particular router and then have that ARP request forwarded as normal broadcast. But since we don't have a lot of migrations going on at the same time, this will be very limited. This particular implementation does require a couple of features from the OpenFlow implementation. It requires support for the normal output queue. It requires to be able to match on the layer 2 header as well as the IP addresses inside our packets. And it would be nice to have metering in order to prevent software bugs from causing broadcast storms directed at individual customers. Sorry, unicast storms in this case. All of these are features that are not available in our current implementation. So to conclude, we can actually do this in theory, but what we can actually do in practice really depends on the actual implementation. The OpenFlow spec defines a lot of very useful features, but most of them are defined as optional. So if a vendor tells you they implement OpenFlow 1.0 or 1.2 or 1.3, you still don't know anything because most of the stuff is optional to implement. We would like to extend this further. We're working with our vendor to get some of the missing features implemented. We're also looking at IPv6 because some of these issues, like the spoofing problem, also apply to IPv6. So we would like to implement a similar solution for IPv6. We also look at implementing OpenFlow for all our traffic streams, so have layer 2 flow rules for all traffic, MAC address to MAC address. We've seen some designs of internet exchanges where OpenFlow rules were set for all layer 3 flows. We don't believe that scales, so we would only be looking at the layer 2 header and implement flow rules based on that. And lastly, we're also looking at some alternatives such as eVPN, which would offer similar functionality, just implemented in a different way. I'd like to close off with some tips for people that are starting to look at OpenFlow. If you're an operator and you want to run OpenFlow in your network, be sure to limit control traffic. Usually this traffic is CPU forwarded, so if you have a lot of traffic from users that will be forwarded to the controller, you will soon run into trouble if you try to scale this. Another thing we've thought of is controller placement. If you place your controller in your management network and you actually use it to forward traffic, and then you suddenly get a dependency of your management network on your production network and the other way around, which is not really desirable. And if you put it in your production network, you have to be careful not to create a feedback loop situation where you would actually require a flow rule in order to reach your controller. Then if you're a vendor, please design your implementations for use inline. I think many operators, at least we, won't be replacing our entire network with OpenFlow, so we really see it as an additional feature in a network. So we'd like to see it implemented that way, sort of like an ACL on steroids or FlowSpec on steroids. Please, if you implement it, implement as many fields as you can. The whole promise of OpenFlow was that it would give operators the flexibility to do everything they wanted. And well, if you only implement the very basic part of the spec, then there's very little we as operators can do with it. And finally, make sure to protect the control functions of the router of the PE. Make sure you forward control the traffic in hardware or at least rate limit it. And that's all I had. This work is building on a paper by two students from the University of Amsterdam, Hani Bagheri and Victor Boutonneau. If you're interested in reading more, I recommend you look at their paper. Any questions? No one?
Thank you.